All right, so any questions? Yes? All right, tell me what chapter we're in, first of all. That makes sense. All right, 3.7. All right, 3.7, which number? Number 2. So n factorially stuff. So prove 1 times 1 factorial plus 2 times 2 factorial up to n times n factorial equals n plus 1 factorial minus 1. Well, that's a cool formula. So sum of n times n factorial gets you to the next factorial minus 1. So what's the proposition we're working with? Let P of n be the proposition and just all of this stuff. Or we could write a summation symbol. So the first comment I want to make on this, the way the problem's actually worded says prove that if n is bigger than 1, then all of this is true. And it can be tempting to say, okay, so we're being asked to show that n bigger than 1 implies all of this stuff, right? Don't go down that path. In general, that's not what you're asking, right? What we're asked to show is simply to prove that P of n is true for all n. Is it bigger than or equal to 1? Yeah. Right, so even though it says prove and then it's got all the stuff after the word prove, you're free to rearrange that however you like, right? And in this case, the real thing we're trying to prove is that this equality is true, and we're trying to prove it for n bigger than or equal to 1. So don't necessarily start with, you know, step 1, n is bigger than or equal to 1, because that's the hypothesis, okay? So you can be as specific as you like about what you're trying to show. So we're trying to prove this proposition P of n for n bigger than or equal to 1. So what's the first thing we have to do to use induction? Base case. So what's our base case going to be here? P of 1. And that says 1 times 1 factorial equals 2 factorial minus 1. And 1 times 1 factorial is 1, and 2 factorial is 2 minus 1 is 1, and those are equal. So P of 1 is true. All right, so assume P of n, and we want to show P of n plus 1. All right, well, we know what P of n says. We've just written it down twice already, but let's put down this ignore, and let's write down what P of n plus 1 says, so we know what we're trying to get to. So we're trying to show 1 times 1 factorial plus 2 times 2 factorial plus n times n factorial plus n plus 1 times n plus 1 factorial equals n plus 2 factorial minus 1. That's what we'd like to get to. And we know that all of this stuff, because we believe P of n, this can be replaced by n plus 1 factorial minus 1. So now the question is, can we show that n plus 1 factorial minus 1 plus n plus 1 times n plus 1 factorial somehow equals n plus 2 factorial minus 1? And it's a big gory algebra puzzle at this point. But let's continue with our scratch work. And we'd like to show that n plus 1 factorial minus 1 plus n plus 1 times n plus 1 factorial equals n plus 2 factorial minus 1. If we can show this, right, that's not part of our proof. That's part of our ignore work. But if we can show this, then what we can do is we can state P of n, which is that this equals this. We can add n plus 1 times n plus 1 factorial to both sides. And we can do whatever we have to do to change this into n plus 2 factorial minus 1. And then state that, you know, this sum up to n plus 1 equals that thing, and then observe that that's P of n plus 1, and therefore P of n plus 1 is true. So there's the inspiration part of finding out how we can get from this left side to this right side, and then there's sort of working backwards through that to put it in the formalism of mathematical induction. So depending on how much you've thought about factorials, right, there's not a whole lot we can do with this. But one thing that sort of jumps out, perhaps, is we've got an n plus 1 factorial here, and we've got an n plus 1 factorial here. What happens if we factor that? So we could get n plus 1 factorial times 1 plus n plus 1. And we still have this minus 1 we have to keep. So I'm just showing what the left side's equal to. And I don't know if that's going to help us or not. Probably not. Well, what's 1 plus n plus 1? So all of a sudden, n plus 1 factorial times n plus 2, that's n plus 2 factorial. And we still have the minus 1. And that's what we were going for. So how do we turn that into what we wanted? Okay, this is our scratch sheet. P of n is true, and that says that's what P of n says. Well, let's just add this thing to both sides. So that's equal to the right side with the same thing added, n plus 1 factorial minus 1 plus n plus 1 factorial. That's just algebra. That's just taking this term and adding it to both sides of this equality, right? And we have this equality because P of n is true. So we add the same thing to both sides. Well, we know secretly that this is going to be the left-hand side of Pn plus 1. So now we want to turn this into the right-hand side of Pn plus 1, which is this, right? Well, we had a way to do that already. So this right-hand side, just go ahead and repeat what we did in our scratch work. N plus 1 factorial times 1 plus n plus 1 minus 1. That's factoring out n plus 1 factorial. This is combining 1 plus n plus 1 to get n plus 2. And this is properties of factorials. So this sum is equal to that, and that's p of n plus 1. Therefore, by mathematical induction, p of n is also true for all n bigger than or equal to 1. And so if you just see this, it's kind of like, where did that come from? I don't know, right? Because we got 2 pages of scratch work that went into it. So that's the idea for most of these. This one's more difficult than a lot of them because it doesn't seem obvious, right, how we're going to get from, you know, in our case, from this to this. But there's only so many things you can do with factorials, really. You can factor things out, you can combine terms, but you can also use this fact that x factorial times x plus 1 is the same thing as x plus 1 factorial. And that'll pop up in a lot of these kinds of questions. Does that help? Cool. All right, any other questions? Yeah. Oh, I'll come back. Prove that a to the n minus 3 to the n is a multiple of 5. Didn't we do this yesterday? You and I? You talked to me about it. I talked to you about it, okay. So Pn is the proposition that a to the n minus 3 to the n is a multiple of 5. And we want to prove P of n for all n bigger than or equal to whatever the natural numbers are. Let's just do it bigger than or equal to 1. It's true for 0, but it's kind of a silly case because it's 1 minus 1. So let's do it for all n bigger than or equal to 1. So what's the base case? We can start at 0, that's fine. So P sub 0 says, so what does it say?
That 8 to the 0 minus 3 to the 0 will equal 0.
Well, P0 doesn't say that it's equal to anything. What does it actually say about 8 to the 0 minus 3 to the 0? It's a multiple of 5, perfect. So to know whether or not P0 is true, we can compute 8 to the 0 minus 3 to the 0. That's 1 minus 1 equals 0, and is 0 a multiple of 5? Yes. So P0 is true. So we got a base case. Okay, now we want to assume P of n. And P of n says 8 to the n minus 3 to the n is a multiple of 5. So mathematically, how did we write that something is a multiple of something else? Say again? Yeah, mod 5 equals 0. How else could we do it without mod? Something even simpler. No division, even simpler. 5 times n, right? So 8 to the n minus 3 to the n is equal to 5 times something. I'm not going to use n because we're using n. Let's say 5 times k, where k is an integer. Okay, that's what we mean by being a multiple of. So a to the n minus 3 to the n is equal to 5 times some integer. Okay, over here, ignore. We want to show that a to the n plus 1 minus 3 to the n plus 1 equals 5 times some other integer. That's our goal. If we can do that, then p of n plus 1 is also true. And the only thing we know is that this statement is true, p of n. So how can we turn a to the n minus 3 to the n into a to the n plus 1 minus 3 to the n plus 1? I don't know. But there are only a few things we can do. So this is more scratch work. We're trying to get to this. We can't really do subtraction when we have powers in there, right? We can't just subtract and get 5 to the n or something, because that would be nice, but it doesn't work that way. So there's not a whole lot of hope of combining these terms or these terms. But can we change some part of this to look like some part of this? Yes, let's multiply both sides by 8 and see what happens. So 8 times a to the n minus 3 to the n is going to be 5 times 8k. It's still going to be a multiple of 5. And 8 times a to the n is 8 to the n plus 1. And 8 times 3 to the n is just 8 times 3 to the n. And I don't want to keep writing 8k, so I'm just going to switch to k prime. It's still a multiple of 5, right? So I've got my 8 to the n plus 1. I've got a 3 to the n times 8. I'd like a 3 to the n plus 1. So how do we get from 3 to the n to 3 to the n plus 1? Multiply both sides by 3. Now, if I multiply this whole thing by 3, I'm going to tweak out my 8 over here. But here's the... There's no gentle way to say this. It's a really subtle trick, and you found it. Here's the insight. 8 times 3 to the n is just 3 times 3 to the n plus 5 times 3 to the n. Right, we're just breaking it out into 2 pieces. But if you think about this, and think about this, and do some substitution, you should find some happiness. So let me leave it there for now, because we got a couple of days before your homework's due. But think about this property, and think about this expression, and do some substitution, combine some terms, add some exponents, and see if you can get it into something that looks like that. And once you get it to look like that, then you go back and you add the mechanical steps to formalize the induction. But play with that. All right, did you have a different one?
Yeah,
6. Generalized Demorgan's law. We were going to do that today, so I won't be grading that one. But yeah, let's go ahead and do Generalized Demorgan. because that's what we were leading up to yesterday. Yesterday?
Yeah, I had that weird, like,
Yeah, you were trying to,
like A to the N.
yeah. That's what we were working on when class ended was De Morgan's for n variables.
Yeah,
And you had a shortcut for
yeah, and it wasn't,
replacing something with the complement of a bunch of n's.
yeah, it wasn't correct syntax.
Yeah, but it was the right idea. So let's just play with this. Let's just play with it for a minute, okay? We know that AB bar equals A bar or B bar. Maybe I should do this a different way from what they ask. All right, we'll do a different one from what the book asks, so you can still do the one for the book. Let's use this other form of De Morgan's theorem. A or B bar equals A bar ended with B bar. So we know this is true. This is De Morgan's theorem. And we'd like to show that this is also true for 3 variables. So we'd like to show if we OR 3 things, it's like ANDing their 3 complements. Well, we know this is true, whatever B is, right? So if we were to let B be, something, we should get A bar ANDed with that same something bar. That's De Morgan's theorem. Okay, it doesn't matter what A and B are. They're ultimately a true or a false. So suppose that instead of just using the variable B, I use B or C. Then just plugging into De Morgan's theorem for 2 variables gives us this equation. A or B or C, all bar equals A bar, ANDed with B or C bar. Right? But since we know De Morgan's theorem for 2 variables, we can say B or C bar is equal to B bar ANDed with C bar. And bingo, there's De Morgan's theorem for 3 variables. Because this is just A or B or C. And this is just A bar, B bar, C bar. So can we do that again to get De Morgan's theorem for 4 variables? Well, we have A or B or whatever bar equals A bar, B bar, something bar. So let's make this C or D. And now this side, C or D bar is equal to C bar ANDed with D bar. And we've got De Morgan's theorem for 4 variables. All right, because everything's associative. So that's that, and that's that. All right, is that okay with everybody? So if you believe that that's all legal, then we're probably pretty sure that if we wanted to do this for 5 variables, we could do exactly the same 2 steps. We could replace D with D or E. We could replace D with D or E. We could use De Morgan's theorem on D or E bar to get D bar and E bar, and then we'd have De Morgan's on 5 variables. All right. So now the whole challenge is, well, what if you want to do it on 6 variables? Right? You can go through the steps, and now you've shown it for 6, but you haven't shown it for 7 yet. And if you want to show it for 1,000,000 variables, you've got to go through this pair of steps 1,000,000 times. And then you're still not done because you don't know if it's going to work for 2 million. So mathematical induction comes to the rescue and says, hey, I can help you do this in general. So we have to do some formal things. So let P of n be the proposition. And I'm going to subscript my variables now so I don't have to use A, B, C, D, E. And which way were we doing this? A1 or A2 or up to AN bar equals the AND of their complements. So Pn is the proposition that De Morgan's theorem works for n variables. We want to prove P of n for, and let's just go bigger than or equal to 2. It's trivially true for n equals 1. It just says A1 bar equals A1 bar. But let's prove it for n bigger than or equal to 2. So is P of 2 true? Yes. That's just De Morgan's theorem. If someone didn't want you to say it's true because De Morgan's theorem is true, how would you actually prove P of 2? It's hard to distribute with a line on the top.
In the book it has it as a little,
Oh, the little knot thing. Yeah, but you can't distribute that, right? If you did, then you'd actually get something different than the right-hand side. You'd actually get not A1 or not A2. Yeah, do a truth table. There you go. So you can always prove things, right? If you don't know the law, if somebody doesn't believe you, you can like write a truth table. Okay, so P of 2 is definitely true. So what do? We assume P of n is true for some n. And now we want to show that this equality holds for n plus 1. So let's just write down this equality. We know it's true because that's P of n. And this is for any n values, right? So A1 plus A2 plus, and let's write AN or AN plus 1. All right, so I'll put back my red blobs. All right, so I'm adding n minus 1 terms, then I'm adding this extra term, which is these two things ORed. And so I should get the AND of the complements of those n minus 1 terms ANDed with the complement of this OR. All right, so this is AN or AN plus 1. And now we can use De Morgan's theorem on two variables and show that this is AN bar ANDed with a n plus 1 bar. So that just comes from knowing P of 2 is true. But saying that this is equal to this, that's exactly Pn plus 1. So the proposition is true for n plus 1. Therefore, it's true for all n bigger than or equal to the base case. So question 6 in the book is slightly different. It's a different version of De Morgan's where you have the complement of the AND and you show that that's equal to the OR of the complements. But same idea. So we can use induction in lots of different situations where we understand something intuitively and we want to formalize it. For example, we had this formula for a finite set A. The number of things in its power set is just 2 raised to the number of things in A. So if A has 3 elements, the power set has 8. If A has 10 elements, the power set has 1,024 elements. And we can prove this pretty easily for particular cases. Suppose that A is equal to the set, I don't know, X, Y, Z, W. So a set with 4 things. And suppose we know that the cardinality of the power set of X, Y, Z is equal to 8. So we're picking out a really particular case of what would be a more general inductive proof. Suppose we know that this set of 3 elements, its power set contains 8 elements. How would we show, just knowing this, that the power set of A is going to contain 16 elements? Any ideas? We know the power set of X, Y, Z contains 8 elements. What can we say about the power set of X, Y, Z, W? Power set mean? We're going back a few weeks here. Set of all. Say again? Combinations is not exactly the word I want. Subsets, yeah. So combinations of elements, but they're actually subsets. So the power set of A is the set of all subsets of A. So this left-hand side is the number of subsets of A. So the number of subsets of X, Y, Z is 8. You got X, Y, Z, X, Y, Y, Z, X, Z, X, Y, Z in the empty set. So the question is, if we are told this, can we somehow, without too much work, prove that there are a total of 16 subsets of this bigger set? So what does it mean to be a subset of A? It's a set containing some collection of elements from A, right? So let S be a subset of A. There's 2 possibilities. Possibility 1, W is not an element of the subset. If W is not an element of the subset, but S is a subset of A, then S is really just a subset of X, Y, Z, right? It's got to contain only elements that are in A, and we're saying it doesn't contain W, so it's a subset of X, Y, Z. And how many subsets are there of X, Y, Z? There's 8, right? That's what we're taking from this assumption. So if W is not contained in S, then there are 8 possible such subsets. Case 2, W is contained in S. Well, we have a subset of A, and it contains W. So this set is equal to W union some set that's made up of only X, Y, Z. Right? So it's W, sorry, S. So this set is W union with some S prime, where S prime is a subset of A, and S prime doesn't contain W. Well, how many subsets are there of this that don't contain W? There's still 8, right? So if W is an element of S, there's 8 possible such subsets. So the total number of subsets of A is just 8 plus 8, which is 16. And we didn't have to list them off. We simply broke a possible subset into 2 categories. Subsets that contain W, which mean that you have a subset of X, Y, Z plus the set W thrown in. And the number of subsets of X, Y, Z is just 8. And subsets that don't contain W is just a subset of X, Y, Z, and there's 8 of those. And you have to do some formalism to show there's no overlap, but that's pretty easy. And there's nothing magic about the number 8. If we had a set whose cardinality was n, and we add one more element, the number of subsets of that is n plus n, 2 times n. And so we throw in a base case that for a single set we have 2 elements in the power set, and there's an inductive proof. Or there's the framework for an inductive proof. You have to throw a lot of meat on the bones, but that'll get you set up. All right, let's shift gears. So, how many people here are familiar with Towers of Hanoi? Cool. All right, so there's a myth that somewhere in Tibet there's a cave, and in this cave are some monks, and these monks are playing a game. And when the game finishes, the universe ends. So here's a simplified version of the game these monks are playing. And it's called Towers of Hanoi. So what does this look like? You have 3 posts, and you have n disks. So this is just for n equals 3. And your goal is to move the disks to another post. So you want to take all these disks that are on one post and move them all to another post. And you've got the following rules. You can only do 1 disk at a time. You can only take the top disk, so it's like a stack. And you can only, let's say you can't place a larger disk on top of a smaller. I think those are the only rules we need, but I might add more. All right, so we want to move the disks from this post to one of the other posts. All right, so can only move the top disk, which means this is the only disk I can move. And I can't put it on top of a smaller disk, but there's no disks here or here, so I can put it on either disk that either post that I want. Okay, can only move the top. I could move this disk again, but there's no point in that, right? So I've got to move this disk. And I can't put it down here because that violates the rules, so I'm going to put it over here. All right, I can't really move this disk anywhere because it's bigger than any of these. So I could move this disk again, but that's pointless because I just moved it. So let's go ahead and move this small disk and put it on top. And now I'm going to take this largest disk and put it over here. And then I'm going to put the small disk here, and put this one here, and put this one here. Okay, and that took me 7 moves. So that's not too bad, 3 disks. right, you got the idea? So who wants to try to do this with 4 disks? All right. It'll only cost you $5 to play. No. All right, go on this side. Actually, you know what? This might work up here. Yeah. Yeah, the posts come out. Cool. I believe it. Oh, yeah. Cool. Yay. All right, awesome. I'll give you each one of these for your midterm. If there's any way to. Yeah, yeah. Yeah, I'm not going to be able to do that. That's going to be pukey. All right, so, cool. So did you have a method for doing that? Sort of. So the legend is that these monks are working on a pile with 64 disks. And once all the disks are moved, the universe ends. And so it would be nice to know sort of how many moves it's going to take to do that. Let's go back to 4 disks. So let's think about this. Yes? Number of posts for this is always 3. There's lots of cool variations on this. But for this one, it's just always three posts and disks. So we know how to move 3 disks, right? And we can do that in 7 moves. Okay, now someone asked you to move 4 disks. Here's one way to do it. Both of these posts are empty. This bottom disk is the biggest of all. So whether or not this is sitting on a post, I can put any of these other 3 disks on top of it, right? Because it's the biggest one. So if I just leave this big disk exactly where it is, and I just think of moving 3 disks from here to here, I've already done that, right? I know how to do that, and it's going to take me 7 moves. So 7 moves, I can accomplish that. 1 more move, I can accomplish this. And now I just do my simpler problem again. Let's just move our 3 disks from here to here, and I know how to do that, and that's going to take 7 moves. So for 4 disks, it's going to take 7 moves, plus 1 to move the big disk, plus 7 to move the small one, which is going to be 15. So now suppose I have 5 disks. Can we solve this? We can do this without thinking, right? Because we already know how to do the problem for 4 disks. So solve the problem for these 4, move them over here, and then this biggest disk can go over here, and now solve the same 4-disk problem again, moving from this post to this post. And there's our solution for 5. And this is going to take 15 moves to move the top 4 disks, plus 1 to move the biggest disk, plus 15 to move the top 4. And that's going to take us 31 moves. So 5 will be 31. And it looks like our general formula is for n disks. What's the general formula here? Two to the n. You're close. No, it's 2 to the n minus 1. So 8, 16, 32 are the powers of 2. And can we prove that inductively? Absolutely. How? Suppose we know that to move n disks takes 2 to the n minus 1 moves. If we want to move n plus 1 disks, how many moves does it take? Well, it takes 2 to the n minus 1 to move the top n disks over to an empty post. And then it takes 1 move to move the biggest disk to our target post. And then it takes another 2 to the n minus 1 to move those top n disks to the target post on top of the biggest disk. And this is 2 to the n plus 2 to the n is 2 to the n plus 1. Minus 1 plus 1 minus 1 is minus 1. But here again, we not only have an inductive proof that this formula for the number of moves is correct, but in fact we have an algorithm now for solving this puzzle. And if you have 8 disks, and you want to move them from one post to another, all you got to do is solve the 7-disk problem twice. And if you have a friend who knows how to solve the problem for 7 disks, you say, hey, can you move these 7 disks? You move the big disk, you say, can you move these 7 disks? And you're done. Right? And your friend solves the 7-disk problem because they have a friend who can solve the 6-disk problem. But that friend actually has a friend who can solve the 5-disk problem, and so on. And eventually one of them has a friend that can solve the most famous 1-disk problem. Can you move this from here to here? Yeah, I can do that. There you go. So here's a piece of C code that'll do this. We'll go over this again tomorrow, but there's a function tower that says move 4 disks from peg 1 to peg 2, and that peg 3 is unused, right? So this will move from peg 1 to peg 2. And this is basically the guts of the algorithm. If we're trying to move num disks, simply move num minus 1 disks from whatever the original post is to whatever the open post is, and the third post is unused, and then move 1 disk from our source post to our target post, and then move the disks from our open post to our target post. And this is the base case where our friend no longer has to ask another friend. If you only have 1 disk to move, just move from the from post to the to post. And the move routine just prints out that you're moving from one post to another post. So there's a solution for the 4-disk problem. And you can actually play this out, move from disk 1, post 1 to 3, 1 to 2, 3 to 2, and so on. But if we wanted to do this for the end of the world, there's how you do it for 64 disks. And if you follow all those instructions, eventually your 64 disks will be on the second post. And we almost don't have to think about how to do this, right? The algorithm for doing this is it's kind of weird to think about, right? But if you approach it like this, it's kind of brainless, but it works, right? And that's characteristic of these induction kind of proofs and these inductive kind of processes. It almost feels like you're not actually doing any work, right? That's when you know you're doing something inductive. All right, so we'll look at this a little closer tomorrow because we kind of ran out of time there. And I'll talk a little bit more about some inductive processes, and then we're probably going to move on to number theory next. So bring some homework questions tomorrow, and we'll go on from there.